Hey everyone. My name is Yuan, and welcome to the XCamp USACO live solution for Gold Division. And my name is Yuan, and I'm the co-founder of XCamp. So today we're going to cover the following different sections. So I'll first do a quick introduction, and then after that, we will have our Grandmaster teacher, Max Zhang, to talk about the contest tutorial. And after that, we'll go over some of the class arrangement and to introduce what we are offering as classes. And after that, we'll also give you some tips about the next USACO. So XCamp Academy is a Silicon Valley-based coding academy. We offer all the classes starting from beginner level all the way to master level, even as high as national team level. And we have a curriculum developed by seasoned coach, IOI medalists, USACO veterans, and NOI medalists, and also some senior engineers in tech company as well. So our teaching hierarchy have been proven. We aim to build very solid knowledge of data structure and algorithm. And we want all our students to have really good knowledge system. All the topics can get interconnect with each other and build up solid problem-solving skills. And we have 4 USACO campers last season and one the season before. And in the December competition, we have 2 students entered top 2 of the 2 students out of the top 10 in the US in platinum level. Overall speaking, we have 3 section of the class at XCamp. The first part is about the beginner level. We want to build up the interest and love in coding for students. And the second stage is more about algorithm and data structure foundation. In this part, our focus is to systematically to build up the basics and also the logical reasoning behind all these classic algorithms and data structures. And at this stage, our focus is not competition yet. It's all about knowledge complete. And the third stage, for the students who are very passionate about competition, we will get you started in competition with Grandmaster classes. And we will have our coach to help you too. And we will provide you with the best resource. We will be able to work with coaches, but in the same time, you will get access to a strong community with several campers every year in the same class. And for the students who only want to reach a certain level at competition, and then you may have other focus, that's fine too. We strongly believe that the skills and the knowledge you learned in the second stage, which is a fundamental stage, will prepare you really well for your future life, no matter it's in academia or industry. And essentially, I typically call it a lower bound of a life. At least you'll be an excellent engineer in the best tech company, right? So essentially, that's our philosophy and what we are believing and what we are hoping for. That's all. So I will hand over to Max to talk about USACO Gold province. And Max is ACM ICPC World Finalist, and he's one of the best coder I've ever known. Yeah, I'll give it to you.
Yeah, thank you, Yuan. Yeah, I will go ahead and share my screen so we can start talking about the problems. So, all right, hopefully everyone can see okay. All right, so the first problem, so our first problem was this string problem. So it's about find and replace. So I'll briefly describe the problem. So the idea is that we're given a string. Let's say our string is like A, B, A, B, or actually it's initially always A. And we go through a series of transformations. The transformations are of the form where we find some character. And we replace it, all instances of this character we replace with some word. So for example, the first operation might be that we change every instance of the character A in our string to the word B, C. And then next, maybe we'll take all occurrences of C and transform it to A, D. And then our third operation might be that we take all occurrences of A again, and we transform them into E. So in this case, if we were to apply these transformations, our string would be first A, and then we change all the instances of A, which is just one character A, to B, C. And then we change all instances of C to AD, so it becomes BAD. And then finally, we take all instances of A and change it to E, so it becomes B, triple E, and D. And actually, let me give one more example, one more operation, just to show that we replace all characters and not just one of them. So if I have an operation that changes E to F, then this becomes, all the E's get replaced with F. So it becomes B, F, 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 and D. And so our idea is to kind of basically the problem then gives you they give you L and R, and they ask you to print our final string from L through L to R. Now let's provide some bounds on this problem. So let me see here. So the bounds on this problem are that first off, the number of operations. So number of operations is less than or equal to the 2e5. So 2 times 10 to the 5. Similarly, the sum of the lengths of all the input strings, so the sum of all SI, these are the input strings, is also less than or equal to 2e5. And also because we have to print this, right? The final string could get exponentially large. So we clearly cannot ask for too wide of a range of L through R. So they also have a constraint that R minus L plus 1. So basically how big the range we actually have to print is also less than or equal to 2e5. So those are the bounds we're working with. And I guess also for simply, I also only mentioned one subtask. There's a subtask for this problem where all of the above are instead less than or equal to 2000. Okay, so let's talk through some ideas for this problem. So first things first, for the sake of simplicity, because I don't want to specify in my complexity when we're talking about operations or S or R minus L plus 1, they're all like they're all the same value, like 2e5. Then for the sake of simplicity, I'm just going to say that all of these are equal to O of n, or just like, basically, I'm just going to say like n is like our 2e5. So this way I can say things like O of n or O of n squared. I don't have to specify like S times number of operations or S times quantity R minus L plus 1, just to keep things simpler. All right. So what is an idea here? So when we look at this problem, clearly we cannot simulate the operation, but we want to kind of gain an understanding of how these operations, or kind of what the structure of these operations form. So what I mean by that is like, for example, if I have A transforms into the string BC, then if in the future I have an operation that changes B to ED, then I might have kind of like this character B changes to E and D. And then let's say later on, I also have an operation that changes C to like say BAF. Then this C character also gets changed to BAF. And then let's say even further down the line, there's an operation that changes, I'm going to keep the example shorter by using a letter that I used before. I'm going to change the D for D. So let's say later down the line, there's another operation that changes D to say EF. Then what I'm going to do is I'm going to say this D gets changed to EF, but this is also a D here. This also occurred before our operation involving character D. So this will also get changed to EF. Right? So I drew this very suggestive diagram here because the structure we have is essentially a directed acyclic graph, right? So it's directed because these edges have orderings, have arrows. So I'm going to say directed acyclic graph. And it's a graph. And to show that this is acyclic, we just realized that the way I define these nodes here, what I've drawn is these are basically the input nodes. This is like the initial, like 0. This BC comes from I have another operation. This BC comes from my first operation. This ED comes from my second operation. This comes from my third operation, and this comes from my fourth operation. So basically, I'm always drawing edges from an earlier operation to a later operation to describe the behavior. So it's a directed, it's an acyclic relationship. I'm not going to point from a later operation back to an earlier operation. And for clarification on how I'm choosing to build this graph, if later in the future there is another operation where like say E gets transformed into BC, then I'm not going to draw this back around to this. I'm not going to loop it around. I'm going to create a new version of BC that happened at time 5 instead. So that's clarification on how I'm building this graph. It's not defined just based on the string, it's also defined based on the time. Now, if we were to draw this graph, we can start to see some benefits of this graph. So essentially, let's start from the bottom, right? If our situation is that we've reached like this this final node here, like we follow like the idea is that this node, right? This node represents the string BC. It represents 2 characters. Now up here, EF, we had an operation that changed E to BC, right? So that means that this string is actually going to be BCF, right? It's EF got transformed into BCF. So this is actually length 3. And the way we calculate that is we just iterate over each of its characters. And if a character has a corresponding edge pointing to something else, then we add the kind of like the subtree size. It's not really a tree, but we basically add the size of the total size of the string accumulated at the other arrow that we're pointing down to. So this is 3. Basically, this is BCF. Up here, ED becomes, remember we replace the D with the EF, right? So it becomes ED becomes EEF, and then the other E got replaced with BC. And so actually this graph is a little bit incomplete because this E actually has an edge as well. This E is also affected by BC. So in general, our construction of our graph is that every single character has an outgoing edge to the next most recent operation with a future timestamp, right? So this E would still exist that was created at time 2 is going to be affected by this time 5 operation. So therefore, in total, the subtree the size here is going to be 2 from this E. This E is going to transform into 2 characters, plus D comes from here, so it's going to be 3 characters. So it's 2 plus 3, so this is going to be length 5 string in total when expanded. Right, we can kind of resolve this in a similar way. So B and A are not affected by any future operations because no operations affect the character A or B after time 3. D is affected though. D gets transformed to EF, and this is a size 3 node. So this becomes a total of 2 plus 3 is 5. Coming back up to here, I'll cut to the chase. So like we have B becomes this size 5, C becomes a size 5, so this is a total length 10, and this would be also pointing down, so this is also length 10. So why am I describing the sizes? This basically tells us that our total string is of length 10, right? And now, let's say I want to pose the following question. Let's say I want to find the kth character. Let's say I want to ask, what is the kth character, right? So to do that, well, here's the idea. With a structure with the sizes computed, I can start here at the top. And I can say, okay, I know that A will eventually expand into a string of length 10. So let's just go down here to BC. Okay, so BC is going to expand into a string of length 10. Specifically, the character B is going to expand to a string of length 5, and the character C is going to expand into a string of length 5. Now, let's say that we're looking for the 5th character. Then we know that the 5th character is going to be contained because B expands to 5 characters, right? And well, 5 is less than or equal to 5. We know that the 5th character is going to be like down this path. It's going to be within this string that replaces B. It's not going to be in the second half because the first half is already going to contain the 5th character. So we go down this path, right? So I'm going to go ahead and trace the path we are following here. In terms of implementation, this will look like some sort of DFS, some sort of recursive method maybe, or maybe just a loop, depending on how you implemented this. So now we're here. we're at the string ed, we're still looking for the fifth character. E expands to 2 characters and D expands to 3 characters, right? Because it points to 2 and 3. So the fifth character is going to be on the right. So we're going to follow the path here. Now we have EF. EF expands to 3 characters. EF is 3 characters long, specifically E becomes BC, and F becomes, well, F doesn't become anything. And it's also important to specify that here we are looking for the fifth character, the fifth character, the fifth character. But here, we're not looking for the fifth character in here, right? Because, well, EF is not even 5 characters long. We're actually looking for, it would be the third character. And the reason why is because we follow the path of character D. So we already said that the first character E, which expands into 2 characters, those do not contain our character that we're looking for. So we can kind of so we're really looking for the third character in this string, which is the fifth character overall, because there are 2 characters in that the E expands into. So we're looking for k equals 3 here. And now we see that k equals 3, because this E transforms the 2 of them, so it's not going to be down here, it's going to be the F. So we know the fifth character is F. So yeah, with that procedure, we can recover a single character. So with this structure, this immediately takes us to an n² solution. So this solves our first subtask, right? Because we can simply iterate over all characters from L through R. For L through R, each character, we just call our procedure. Like maybe our procedure is called df for all I in L through R, we just call our method dfs of I or something for the root and find our character. And this graph is of size n, right? Because there are O of n states. So this is an n² solution. Now, this is of course not fast enough, so we gotta do a little better than this. So one immediate idea is that it's clearly a waste to call DFS repeatedly from the top for each character. So we should be trying to do this in one traversal. So the idea behind one traversal would be that it would be that if we're looking for a range of 2 through 7, then when we DFS, we might find the second. Say we follow some path, and we find the second character. After the second character, we're going to backtrack up and then go down to find the third character and then find the fourth character and so on and so forth. So basically, we're going to kind of do it all in one DFS and not go all the way start from the beginning again each time, but instead kind of backtrack where we can and find the next character. Unfortunately, just doing this, you can still end up with n², even if you do it all in one traversal. At least the way I've described right now. There's something else we have to do. And to give an idea of what the problem is, let me give you a test case. Let's say that the case is that A becomes AA, and then let's say the operations are A becomes I'll just skip to the chase. Let's say A becomes A blah blah blah, O of n times, maybe n over 2 or something. And then we just spam the same operations of change A to the character B, change B to the character C, change C to the character D, change D to character A, and we just repeatedly spam single character operations. Then our graph is going to look something like this. It's going to look like A goes down to A, O of n times. And then each of these characters are going to have an edge pointing down to the next character B, and then C, and then so on. And this is going to be we're also going to have an O of n length chain here. And now you can see that if we do a DFS, with backtracking, the problem is that if we come down this route, we have to go all the way back up to here, go to the next character A, go down the same chain again, come back up the same chain, go to the next A, go down the exact same chain again, and we visit this O of n chain O of n times for n². So your intuition might tell you, okay, why not just compress this entire chain into one link. And so what I mean by that is B to C, C to D, D to A to E, just compress this into B to E, right? Why not just do that? And actually that is the key to getting better complexity, is just compress these short links, compress these one character links, compress single character. It's not immediately, I don't think it's immediately obvious why this makes it faster, it makes it linear time. So let's talk about it. So after we compress to a single character, in our example here, this would just get compressed into like, this would just compress to, actually, so our compression should also include this A through B. So it actually becomes A to E. And so therefore our graph over here would just be a single node E. And so now we would just be doing O of N, because for each character, we just go down one time and we reach the final character. So how does this work? So in order to show this is linear time, let's look at it this way. So first off, I'm going to not worry about kind of like the tail end. So I'm not going to worry about finding the L or the arc, because for finding like the L or the arc, like the ones on the tail ends, this only happens like twice, right? There are only two like tail end characters. So we're allowed to do like O of N work here. So the issue is that like I want to put a bound on, let's say I'm in a current node and I'm finding some sort, and I'm trying to recover all the characters from X to Y, where like L is less than or equal to X, is less than or equal to Y, is less than or equal to R. This is what I want to bound. I want to make sure this is O of N work. And so the idea is that after I compress the single character operations, if I were to go down a link, there are two possibilities. Either I'm just like done, right? I reached the final character, E or whatever. So case one is I just terminate. I reach the final character. And this would just be, this is just O of one, like stuff, right? Or case two, I get longer, or I get a longer string. So if case two is I'm going from like, for example, A into like AB. Now in this case, there's an extra, this string got one longer, right? This string got the string length, the length increased by one. And the argument I'm going to make is that this plus one, this extra length, I'm going to attribute it to the cost of one of these values between X and Y. So what I mean by that is that basically the reason I'm traversing down this is because I know that like X through Y is like going to be contained inside this like subtree, or is within like the rest of this graph, right? So the idea is that whenever I go down and I get a longer string, at least one longer, each of these new characters is kind of like it can be attributed to the cost of one of the characters inside our range. So if like, for example, like it was just A, it'd just be X. If it was A and B, it's going to be at least like X and X plus one. A, B, C is going to be at least like X plus one, and X plus two. And if later this C expands into like D and E, this can be attributed to the cost of like X plus three, or X plus two and X plus three. Or this D would not be a new character, but this this new character means we're at least on X plus three anymore. And so by that argument, if every single like new expansion can be attributed to one of the characters inside a range, and our range is only of size O of N, then we've also provided a bound on like the number of edges we traversed, which is O of N. Yeah, so just to reiterate again, so to clarify, so the reason I'm talking about it within X and Y is because this is the case when this entire like thing, when this entire like set of nodes is contained within our range, like some X, Y between L and R. I already said that like on the edge cases, on the edges of like L and R. So like if for example like X plus two is not within like our range, then that's considered like the edge case, like on the leftmost and the rightmost. And there only are two edges, the leftmost and rightmost. So we're allowed to do O of N work on the edges. We just need to make sure that the work we do in the middle, like when we're exploring stuff that are strictly within our range, is all bounded. Yes, to recap, we are constructing this graph, and actually for clarification on how to construct this graph, you can, for example, just iterate backwards from the last operation to the first operation, and then for each operation, iterate over each character of the input string, which is all bounded by O of N, and for each character, if you see like if for each character, just look in like a lookup table of like what was the last operation you just processed, and draw an edge to that. This graph can be constructed in linear time. And then the compression can also be done in linear time. Compression can be done similarly when you're traversing from the last operation to the first. Just compress the, like basically if you're going to add an edge from one character to one character, just like instead add it to like the character at the end of the chain that you maintain. And then after that, well, once you make that compression, the DFS part should also be O of n. All right, so that's problem 1. Any questions on this problem? All right, and I will also come back to this. I will also come back to it at the end if anyone has questions. But for now, let's move to the second problem. So the second problem was it was about these like binary strings. It was about lights. Basically, we have here. Let's provide some bounds. So we have a lights 0, 1, 0. Let's say these are the slights. 1 means the light is on, and 0 means the light is off. So this is a set of 5 lights. And we also have these switches. Like let's say our switch is like 1, 1, 0, 1, 1. So that means that initially these switches are enabled, these switches are enabled, and these switches are enabled. And so we can do a series of operations. So an operation is this 3-step operation, kind of contrived. Basically, step 1, I'm allowed to change. I actually have to change. There's no choice. I must toggle one of the characters or one of the switches. I either turn the switch off or I turn some switch on. And I must toggle a switch. So toggle exactly one switch. The second step is that for each enabled switch, for each on switch, I flip the light that it corresponds to. So if after I perform my operation, let's say I perform an operation here and I make it 0, now I check, okay, this is on, this switch is on, this switch is on, and this switch is on. So for each of the on switches, they will affect the corresponding lights and flip them. So this will become 1, this will become 0, and this will become 0 because these switches are affecting these lights. And these lights are not affected because they're in the middle, or they're corresponding to switches that are off. And the third, so that's part 2. Step 2 is switches affect lights. And the third step is there's a rotation. So the switches just rotate over by 1. So they rotate to the right, I believe. So it will go from 11001 to looking like 11100. So that's the definition of one operation. And now the question is just find minimal number of operations. And bounds are very important. The bounds for this problem is they're actually test cases. It's a multi-test problem. There are t less than or equal to 2 times 10 to the 5 test cases. And in each test case, n, which is the length of the string, is less than or equal to 20. And for subtasks, they have n less than or equal to 8 and n less than or equal to 18. Very suggestive subtasks. So let's start with n equals 8. N equals 8. This is kind of just like translate the problem to some code. So you can immediately try, or I guess like whenever you want to simulate something slowly, it's usually like the thought is usually like some sort of thing based on states and dynamic programming. So if we're going to make a very naive state, it would literally be dp of, we have 2 to the n for what the lights look like, and 2 to the n for what the switches look like. And then we literally just perform an operation. So we have like n choices for which switch to toggle. So n choices for the operation. And then we make the corresponding transition. So this is as straightforward as it gets. This is like O of n times 4 to the n pre-computation. And then you can answer the queries in constant time by looking it up in your table. Test cases, not queries, but yeah. So that's for n is equal to 8. If we're going to solve bigger than that, we have to make some observations. So when it comes to, so here's some observations. I guess here's in the order, I'm going to present them in the order that I thought about them. So the first thing I thought about, because whenever I see an operation question, I think it's just nice to kind of characterize and think about like, okay, if I wasn't worried about minimizing the operations, how would I do this? Is there some strategy I can go about this? Because at first I was trying to like see if I can just find some strategy that we can describe for doing this optimally. So I came up with this like upper bound. I'm sure it can prove a stronger upper bound, but the upper bound, there's a simple upper bound of 3n, which is basically step 1, turn off all switches. Step 1, turn off all switches. This takes at most n. Step 2, for each light, for each on light, you can do it in 2 operations, or two operations. Basically, you first turn on the switch, and then the switch will rotate, and you don't want the switch to affect the next one, and so you then turn it off in the next operation. So you turn off the same switch that just got rotated in the next operation. So this is less than or equal to 2n. So this is an upper bound of 3n. Now, this upper bound will come in later. I mean, basically, we're saying that it's like O of n in terms of like how many operations it'll take. So this will come in later. The second observation, second thing we can notice, is we can really try to characterize like what this looks like. So it's a little difficult to deal with this whole rotation nonsense, right? So one idea is maybe we can fix the number of operations. So like do a for loop over the number of operations. Now let's say I fixed the number of operations, then if it's unaffected, then a switch that is initially on at index I is going to flip the lights in the subarray from I to I plus, let's say the number of operations x. It's going to flip all the lights in the range from I to I plus x minus 1. And this is also circular. So if I plus x plus 1 exceeds n, then wrap it back around. So that's the effect of a switch that's initially on, right? And now we notice that let's say we toggle a switch. Let's say we toggle a certain switch on turn 1, or on turn 2, 3, etc. So in general, on turn I, we notice that the effect of toggling a switch on turn I is just flipping a subarray of size x minus I think plus 1. Yeah, x minus I plus 1. That's the effect of toggling a light on turn I. And you can think about it because, like, there's two cases. If you toggle a light that is if you toggle a switch that was previously off, then now it's on, and it's going to affect the subarray of x minus I plus 1, because that's how many turns are left over, including the current turn. And if you toggle a switch that is initially on, then you turn it off. And so now you're no longer going to be flipping the remaining subarray of size x minus I plus 1, which is still equivalent to just flipping the remaining subarray of size x minus I plus 1 again. So this is the effect of doing it. So this is really powerful, actually. This is a really powerful observation, because what this means is that our problem reduces down to given lights and switches, the initial switches, if we fix x, then the initial switches correspond to flip some size x subarrays. And then we want to ask, is it possible to flip exactly size 1, size 2 up to size x subarray to make the lights all the lights off. That's what our problem is reduced down to. And this now, well, what we can do is we can first just go ahead and perform these flips now. Just go ahead and perform all these initial size X subarray flips from the switches, and now we just have some like some lights and no switches on, and flip, and we want to flip 1, 2 up to X. And this now can be pre-computed with a DP, but now the DP is just, we have the lights are 2 to the n possible scenarios, but none of the switches are on. So the switches have been removed from our state. And so our DP can be the turn that we're on and the 2 to the n for what the lights look like. And the transition time also takes n for choosing where to place the current subarray. That this is an O of n squared times 2 to the n pre-computation plus t times I think you can do it in n squared, for example, if you just iterate over the number of turns, and then for each number of turns you have to iterate over all the initial switches and apply like that size flip, and then check the lookup table or look up the DP table to be pre-computed. So this would be the complexity of this solution. Now, before one more nuance here. So I think earlier I mentioned there were subtasks of n is less than or equal to 18 and n is less than or equal to 20. So if you're not careful, this might not be fast enough to pass all the tests. So I think, and I'm speculating because I didn't actually take the contest myself, so I didn't get to submit, but I'm speculating that the way you speed up to n is less than or equal to 20, I don't see there's no easy complexity speed up, but what you can do is if you like pre-compute the DP, but you like only look at states, only do process like states that are true, because this is a DP of like true or false. So if you only process the true states, then you prune a whole bunch of them. So like initially on the first turn, only like the 0 mask is true. And then on the second turn, and then after the first turn is completed, you only have n different masks with like each with like one subarray with one of the bits on. So you have much less states if you like prune it. And I tried running this locally, and this runs pretty fast if you like prune some states. It's like I got it like it's like easily runs in like less than half a second, and it wasn't even. So yeah, there are ways. So you can get this to run pretty much like it adds perhaps 2 to the n, but like it's a good enough constant factor. And the other thing is that also experimentally I derived the upper bound of like 3n is actually a pretty bad upper bound. You can get it's actually much less than that. I think the experimental upper bound I derived was like for n is equal to 20, x is at most 11. So just things like that will get you to a much better reduced constant factor, and then the solution should run the time for that. All right, so any questions on the second problem? So a quick recap. The key observation was we're going to iterate over exactly how many operations will happen, how many turns, and then they become fixed. These operations, these rotations become like effects of flipping fixed size subarrays, and now reduces down to a problem that we can better solve with in mode complexity, which is can we make a mask from certain subarrays of sizes 1 through the total number of operations. All right, any questions? Awesome. Let's move to our last problem then. Our last problem was it's about this cow on a number line. Initially at x is equal to 0, and the idea is that the cow takes a series of moves. So it's gonna be right, left, right, 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 left, right. This might be a sequence of moves, and actually it has to end at x equals 0. So it looks something like this. The cow will go right, left, right, 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 left, left, left. The cal's going to perform some operations, and then in between each of the points, so all the half points, so in between here, here, and here, we're going to keep track of how many times the cal passes that point. So it passes here 4 times, 2 times, and 2 times. And so now the idea is they don't give you the sequence. They give you this final array of what this looks like. Oh, and one more thing, the cal will never go past 0 or beyond like the n. So it will always stay within this range. And so now they give you the final sequence as the input, like 4, 2, 2. And they ask you to count the number of valid sequences that can so number of like different ways the cal can move to generate this this set of values with, so not just any sequences, with the minimum number of turns or direction changes. So when I say a direction change, basically what it means is if a cal goes right and then it goes left afterward, that's a direction change. And if it goes right 2 times in a row, then it's not a direction change. And we want to minimize the number of direction changes. So I kind of viewed this as like 2 different steps. It's like first figuring out what is the minimum direction changes, or not, you don't need to know exactly what it is, but it's nice to know like kind of like what the structure of sequences with minimum direction changes looks like, and then how to count it. So let's analyze how, like, what does the minimum direction changes look like? So let's give a more complex example. Let's say we have an example of 2, 6, 6, 6, and then 4. Now, one way I could do this is I can go right, 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 right. I can go right, left, right, left. So that would be right, 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 left, right, left. So I'll be here now, and I've covered this one 4 times already, and I've covered each of these once. I go left, 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 so like this, and then right, 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 left, left, left again. So this covers a total of, let's see, I covered it once, I walk back over it, so it's twice, back over it 3 times, 4 times. So I need to do one more. So another right, 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 followed by left, 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 and then finally I go left. So the way we can check if we did this correctly is the number of operations we take, number of steps we take, should be equal to the sum. So this is a sum of 24 operations. We have 24 characters here. Yeah, we have 24 characters. Perfect. Okay, so this is I believe this works. I didn't check the exact L's and R's, but yeah, it's the right number of characters. So is this optimal? Well, this takes, I'm going to count the number of segments of contiguous R's and L's instead. So we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 7 direction changes. I believe in this case, it is actually not optimal. And I think I can give one with, yeah, I believe I should be able to give one with like 5. Or yeah, let's see if we can do this. So we go right, 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 and then right, left, or okay. This is getting a little out of hand. Maybe this example is a little too big. So right, right, left, left, left. So now this becomes 1. We've covered each of these 4. These are 4, and this is all 4. So now we go right 4 times and left 4 times, and then we go right 4 times and left 5 times. Yeah. And yeah, this is 24. Okay, and this has 3, 4, 5, 6. This has 5 direction changes. Okay, so we're kind of noticing like we can maybe notice, or we can kind of try to understand like, what is so suboptimal about the first one because compared to the second one. So I think what's suboptimal about the first one is that what we did was we stepped to the right until we got to here, And then we walked over 4 to like completely reduce 4 to 0. And then we walked over to 6. But the second one was a little more productive in that aspect. Instead of like walking over the 4 separately, what it did was it first went here, it walked over the 6 and back to reduce all the 6s down to 4s. And then it covered all 4 of the 4s in one operation, or like in one like direction, like movement from left to the right, without like making multiple changes. So that's kind of what happened here. So I think the way I'm going to describe this, basically, we kind of reduced these 6s down to 4s first by walking over them, and then we grouped all the 4s together in one swift movement, bringing them all down to 2s, and we grouped all the 2s in one swift movement. That's basically what happened. So in general, let's try to come up with an idea for how to do this. So actually, I'm going to make a few simplifications here. First off, because the problem always guarantees that it's possible, we immediately know that each of these values should be even because we pass over each half point an even number of times, right? We pass it over like half many times to the right and half many times to the left because we end at x is equal to 0. So we can reduce the sequence down to 1, 3, 3, 3, and 2. So we're going to divide by 2 to all the values. And we're also going to do this. So actually, and also what we're going to do is instead of this is kind of just a different way of framing it, but instead I'm going to frame it as instead of as like direction changes R and L, I'm going to frame it as like intervals. So it's kind of like what we do is we grouped all the 3s together in like one swift movement. So there's an interval from, I'm going to say from if it's index like 0, 1, 2, 3, 4, 5. Then there's an interval from 1 to 4. So this is like in between. And then that's going to reduce each of these down by 1. So it's 2s. And then we can include all of these in one movement, right? So there's another interval from 1 to 5. And then we reduce all of these down to 1s. And then we include all of these in one interval. And so what that looks like is we have one more interval of 0 and 5. And so we have a total of 3 intervals. Each interval consists of like some traversal, like rights, followed by lefts, something like that. And then, so this will be a total of like 6 like contiguous substrings of like equal characters. So -1 will be 5 direction changes. Yeah, so this analysis, this is kind of like, I guess it's kind of intuitive why this is optimal, because the idea is that when we have large values, like let's say you have like 2 3s next to each other, there's no reason to not include the 2 3s in the same motion, instead of like in the same like sweep of like 1 to the right and to the left, instead of doing each of these separately and then come over here and do it separately. It makes sense to group it together. The premise is kind of like we're grouping together equal elements. And if we wanted to like actually go with the algorithm to find these intervals, we can like start from the maximum AI going down. And then for each like for all the same AI, we group them together to get a bunch of intervals. So we have all these 3s together are one interval. And then now we have, and then they reduce to 2s. We have all these 2s together as one interval, and they all become 1s, and all these 1s are one interval. So that would be an algorithm to actually find these intervals. Now we don't actually need to find the intervals, because that's not what we're trying to do. We're not trying to like solve the minimum count. We're just trying to count how many of these sequences there are. But we've kind of gained some insight into like what's optimal procedures or sequences look like, which is that we're grouping together equal values and like including them in the same trip, in a sense, the same like right, all the way to the right, all the way to the left procedure. So now let's start counting these sequences. These intervals are a little difficult to count like in terms of the intervals. I did try for a while, but it's not a good characterization. So the key to getting a good characterization for this problem is looking at adjacent positions between I and I plus 1, and considering how many times do we cross over from I to I plus 1. Well, let's look at it this way. Let's look at, for example, let's look at going back to our example 1, 3, 3, 3, 3, 2. let's look at here. And I want to know, okay, what does the procedure what look like for coming through here? Because the idea is to like, at some we're gonna go between here, like we're gonna go over here. Yeah, what happens is we're gonna go like across over here, do some stuff on this side, come back over, do some stuff on this side, and go back over. I guess in this case it wouldn't go back over, but if the numbers were larger, like say it goes between like 4 and 6. So these are the divided by 2 versions, by the way. These are the divided by 2 versions, not the original inputs. But we would go over, like we would go over to this side, do some stuff, come back over here, do some stuff, maybe go back over here, do some stuff, and so on. I want to know in the middle, how are we transitioning between these like different sides? And so the idea is, let's say, okay, so I'm gonna put it without loss generality. Loss generality, let's say that AI is less than or equal to AI plus 1. So what this means is, okay, yeah. So if AI is less than or equal to AI plus 1, then the idea is, each time we traverse, like let's see, as I plus 1, each time we have a movement to the right over here, because remember our optimal structure in order to like minimize the number of operations is to kind of like merge equal values together, or kind of get like the values together. It makes sense to include AI plus 1 in the same motion. So it's going to be optimal to move to the right again. And then when we come over from the left, sometimes we might move to the left again, but we're not always able to because AI is less than AI plus 1. So AI might run out. So actually, I'm going to include, I'm going to do strictly less than. I'm going to include the other case, and reasons will become clear later. But yeah, the idea is I'm going to, if I come over from the left, then I want to move over to the left again, but I'm not always able to do that. Specifically, there's going to be AI plus 1 minus AI times, and this is remember again, this is the divided by 2 version, not the original input. So maybe I should put an AI prime to signify that these are the divided by 2 versions. They're going to be AI prime plus 1 minus AI times, where I come over to the right, and then I have to go back over to the right again. And so I claim that if I was just going to like distribute, basically I have a decision where like when I come to the left, I always have to go back left again. But when I come to the right, I can choose to either go to the left or I can choose to go back to the right. And I just need to make sure that I go to the right, AI plus 1 minus AI times. And so basically this is a combinatorics problem, right? I have a total of AI plus 1 times where I go from the right to the left. And I need to choose AI of them to go to the left again. And then I need to choose AI of them to go to the left again. And the other times I would go to the right afterwards. And there's a bit of a subtlety here is that because we had to end on x is equal to 0, on the final time that we come over to the left, if we go to the right, we're going to get stuck. So we have to, on the final time we come to the left, we have to go left again. So it's actually going to be -1 and -1 for these binomial coefficients because the last left movement is going to automatically be assigned or paired with the left movement. So out of the remaining AI plus 1 minus 1 left movements, I need to choose AI minus 1 of them to be left movements afterwards, and the other ones are going to be right movements afterwards. And so similarly in the other case where AI is greater than or equal to AI plus 1, it's going to be that from I to I plus 1, if I move to the left, I'm going to move to the left again. If I move to the right, I try to move to the right again, but I cannot always. I'm not going to be able to move to the right again in AI minus AI plus 1 times, right? So it's going to be another combinatorics problem again, where we have AI choose AI plus 1. And this time there is no -1 because when we move to the right, hold on. Sorry. Yeah, it's because when we move to the left, when we move to It's a, hold on, let me see here. Oh yeah, the limiting case is when we move to the right. Yeah, so when we move to the right, yeah, some of the times we're gonna move to the left, other times we're gonna move to the right. But when we move to the right, the final time, we can still move to the right again in the future again, because like somewhere along the line we'll be brought back again to the left again. So we don't really have to like force the left, the final like right to be matched with the left. Whereas like here, if we move to the right, if we move to the left the final time, when we move right, we're not gonna have a way to get back to the left side. So that's why there's no -1 in this case. So that's between a single pair of indices. And it's going to turn out that the choice, this counting for each pair of indices is independent for each of these kind of like consecutive gaps. Well, there's no arrow here, but it's independent between each of these. And intuitively, you can think of it as like kind of like what I described here, right? Like in the middle, we're choosing like in what order we're going to go to the left or to the right. And then after we go to the left or to the right, we have other stuff that gets processed in some way. And those ways, we don't really know how it's done, but we know that we have to like partition like the left and the right stuff with like our movements in the middle. And regardless of like what we do on the right or on the left, we're going to have the same number of times we cross over this middle part. So the partition is always going to be the same logic. It's an independent counting choice, which means our answer is going to be in total is the product of I from 0 to n minus 2 of the casework of AI plus 1 minus 1, choose AI minus 1 if AI is less than AI plus 1, and AI choose AI plus 1 otherwise. And yeah, that's the entire problem. Yes, to recap, basically the optimal structure is we want to always keep like grouping stuff together in like the same like motion. I guess I call them intervals earlier, but it's basically like continuously move to the right across like the same like set of values grouped together. We want to group them together when possible. So we look at like in between like individual adjacent pairs, and we check like basically what the behavior in between the pairs are. I mean, use the logic of like having to like group together equal or like group whenever we can means that like when we move to the right, in this case, we have to move to the right again, stuff like that. And that leads us to this. All right, so any questions? All right. Yeah. So there's also a Q&A session at the end, I believe. So I'll be able to answer, I can answer more like meta questions about like, what I think about like this contest, like difficulty, and also like how to prepare, things like that. So let's go ahead and move back to these slides now. All right. Okay, so hopefully everyone can see. Yeah, prepare for next USACO. So yeah, I think a whole lot of you here are already enrolled in our classes, but if you're not, then yeah, you can prepare for next USACO by enrolling in our classes. There's a whole list here. I'm not going to read the slides word for word, but you can read this information here. You can also go onto the website, the XCAM website, and find information on different classes, and yeah, pick the one that meets your needs. And we also have a mock tests. Yeah, I believe these mock tests are public. So we have public mock tests if you go to tinyurl.com/this link here, and those are offered every month. And those don't, I believe those don't require sign up for a class. So we also offer those as resources. And is that it? Oh, yeah, I guess that's it. Okay. Yeah, so this is what I said before, there's a time for Q&A. So if you have any questions, about it can be about the problems, or it can also be about just like USACO in general, then you can raise them in the chat.
Thanks, Teacher Max. Maybe I can ask a question first because I joined from the previous bronze level, and the bronze levels coach mentioned that he think about the general contest is way more easier than the December. Does anyone have any experience about compare with the December or January? Maybe anyone, because we are a small group, so maybe anyone can share some experience, right, to our coaches. The bronze level, they mentioned that January is easier than the December. What do you think, guys?
I guess while everyone's like typing or thinking, I can also provide my perspective as I've seen the December problems and now I've seen the January problems. I think I mean, on the gold level, I think they're kind of similar. I think they're arguably, like, in my opinion, I thought problem 3 was like was harder than some of the problems that were offered in December. But then also, like, on the other hand, problem 1, I guess, was maybe more straightforward in the sense that you start with a string, you have a procedure that you build a graph for, and it's like very methodical. It's a type of thing that you can train for, and it's versus like maybe like other problems like 2 and 3 I would call more high variance. So those are problems where if you make the right observation, you can do it, but whether or not you make the right observation is up to both how much practice you've done, also just a little bit of like, do you have like the aha moments during the contest? So yeah, I think I think it also, of course, it also depends on the individual, right? Some people are better at certain topics than others, but yeah.
Yeah, maybe some student, you welcome to write down your experience, right? Your feelings about between the December and January, or any trends about the February contest. Yeah,
we as teachers keep an eye on the trends as well. I mean, we do constantly adapt like our class and like how we structure it based on like, you know, what the trend of USACO looks like. So like, for example, right after the December contest, we actually changed how our 602 class homework worked. We changed the structure of the class to make it so more focused on like giving students time to think about the problems and discussing them during class. So we make very adaptive changes in response to the USACO contest as they come out.
Yeah, one student did direct message to me, and he mentioned that he felt both. Would you mind to share some feelings, and if you were looking for some help from Max, feel free to ask him directly. Max is our USACO Grandmaster Class coaches and teachers. Or maybe which problem or how many test cases you have. Feel free to write it down. Share to, or send a message to me or Max directly. No worries about that. Open discussion, right?
Yeah. And I'll just say in general, for anyone who's like worried about like, you know, failing contest, if they're not doing so well in the previous contest, and they think like, oh, am I going to be able to pass next month? I think like in USACO, there is like, I usually think of it more as just like, you know, you pass or you don't pass, right? It's like, if you fail, doesn't mean it doesn't mean you have no chance of, you know, doing well in the next contest. You know, sometimes you see a contest and you just happen to, you know, as I said before, these problems are oftentimes high variance, right? You know, sometimes you just don't notice the trick, sometimes you do notice the trick. And so it's like, you know, it's completely possible that you do well in the next contest, even if you didn't do well in the previous. It's not like you increase your score by a constant like 100 or 200 each time. You can go from not doing well to passing the next contest. And also, like, you know, what we do in our classes is like we train students basically, right? So like the idea is like, you know, with more training, with more exposure to different like tricks, different problems, you gain a better like, you know, problem solving base, and you are more likely to be able to like rederive and think of these tricks yourself, because, you know, practice makes perfect.
I still remember last time I discussed with one USACO finalist, and he told me, remember to write some summary, right? After the recap, after you finish one contest, right?
It's important that you don't let the contest go to waste, right? Even if you don't do well in December, there are things to learn from that. You know, you can think about not just like why you didn't, not just like, you know, how to do the problem, but maybe like, you know, why you didn't solve the problem during the contest. What happened? What state of mind were you in? What things were you thinking about? Or maybe like just like, you know, things you could change for next contest.
That's good. Conclusion. And if some student you are not I'm not sure whether you are current SCAM student, we are providing the one-on-one consulting with the coaches like Max and other USACO Grandmaster level coaches. Feel free to email us. Yeah, or chat on our website. We can schedule the one-on-one consulting with our coaches to see which knowledge gap you have or what kind of knowledge base you need to improve, to the next contest. It's a long journey, right? Not just only one or two contests. Yeah, Teacher Max, maybe we can have 5 more minutes, to let student ask question. And then we can.
I'm looking at the chat here.
Yeah, sure.
See if anyone's got anything. Yeah, it looks like most of the participants left, so I think it might be wrapped up for today.
Yeah, sure. Max, do you know the students? Are they your current student or non-SCAM student? Actually, I cannot tell from their names.
I recognized a few of them earlier. I think the students I recognized have already left, but yeah.
I see.
But yeah, I guess in any case, thanks for coming out today. Yeah.
Thanks for coming. Thanks, Teacher Max. Yeah, have a good night.
Bye everyone.
Bye.